let me introduce our great speaker and great researcher, Professor Koichiro Tanaka from Kyoto University in Japan, with his plenary talk on a high harmonic generation session. So, Koichiro, please load your presentation.
Yeah, may I share the screen?
Oh, yes, please.
Yeah. Can you see this?
Yes, great.
Yep. So first of all, I'd like to thank the organizers, especially Mihail, to give me a chance to present our recent results. And today I'd like to focus on high harmonic generation from strongly correlated materials. And I'd like to thank Dr. Uchida. He's a main researcher in this topic. And the material we obtain from Professor Minor's group, a very nice calcium-2 ruthenium-04. I'd like to show you mainly today the result of calcium-2 ruthenium-04. And this is the today's topic on talk. And I'd like to briefly show what is high harmonic generation in solids, and then talk about the background, why we study strongly correlated electron system for high harmonic generation. Then I talk about the result in calcium-2 ruthenium-04 and summarize. So what is we interested in here is extremely strong light material interaction. And if you consider system Hamiltonian and separating into material part and the light matter interaction part like this, and now we call strong, extreme strong regime should be material part energy is comparable with the light matter interaction part. And if you consider the atomic system and also non-resonant excitation using terse wave or mid-infrared laser, typical energy of the material should be ionization energy in the atomic case. And interaction path should be Rabi frequency defined as like here, dipole moment and the electric field. And when we consider the extreme field regime, we can expect tunneling ionization like this. And under tunneling light and tunneling ionization regime, we can also expect the high harmonic generation. This is a story of the atomic system. But in solids, also people try to see this extremely nonlinear effect. And maybe first report appeared 2001 from Rice University group. So Professor Connor's group. And they showed unconventional nonlinear optical phenomena in several semiconductors. And here I show you two results in zinc selenide. So this one is high harmonic generation. And they used mid-infrared laser around 3 micron to 4 micron. And they obtain this very nice 7th harmonic here, right, like this. And also they reported high sideband generation. And in this case, they use, in addition to the mid-infrared laser, they use also a near-infrared. And they observed this kind of sideband around the near-infrared laser light. This is also a very non-perturbative things. But at the time, the Junkono did not show the power dependence and other kind of things in detail. And after 10 years from 2001, Stanford group showed the very beautiful high harmonic generation from zinc oxide. This is a typical result. And they used also a 3-micron mid-infrared laser. And they did systematic study on high harmonic generation. And they showed the mechanism of high harmonic generation in solid is quite different from that in gases. And for example, cutoff energy, this is a beautiful observation in atomic system, but in solid, cutoff energy is proportional to the electric field. They showed. This is quite different from atomic system. And after that, high harmonic generation in solids opened up a new way to probe the electronic system properties, like band structure and crystal symmetry, and also very curvature, some kind of topological things. And I expect a very beautiful talk from the third speaker. And after that, so many reports appeared in many systems like this. And gallium selenide from the Regensburg and the Stanford group and the MIT, and many reports appeared. But these reports are very limited only in semiconductors, conventional semiconductors. And in conventional semiconductors, now we have a story why high harmonic generation occurs. And this is, I taken this picture from the report from Professor Bampa, Stanford group. And in conventional semiconductors, they showed using theory, and we can apply a 3-step model for high harmonic generation. This is very similar to the atomic system. And this consists 3 steps. And the first electron hole pair are created by Zener tunneling, a kind of pair creation. Then, using the strong electric field of the laser light, these particles are accelerating. And somewhere, recombination occurs. So these 3 steps can describe the spectrum of high harmonic generation, or describe the angle dependence of the polarization things. And people note, under acceleration process, we can expect also some nonlinear current, and this gives also high harmonics. And also a recombination process, we can also expect high harmonics. So in conventional semiconductors, people consider we may separate high harmonic spectrum into 2 parts, like intraband current part and also interband polarization part. But typically, these 2 parts interfere, and spectrum, we must consider both. So motivation of the study is now we have many other class of insulator. This is strongly correlated electron system. And in this material system, interplay among charge, spin, and lattice provides various phases depending on the electron correlations, like a super high temperature superconductor, spintronics material, multiferroics, multi-insulators, so on. So in this symposium or conference, high TC material or superconductor, there is a special session maybe yesterday. And yes, very interesting studies appearing. But today, I'd like to focus more to insulators. So this is insulator and no metallic property. So, but the origin of insulator is quite different from conventional semiconductors. For example, this is a phase diagram of the organic system I taken from the review paper of Professor Kanoda. And by changing the electron-electron correlation energy, and also by changing the temperature, we have many phases in organic system. And like a superconductor, antiferromagnetic insulator, paramagnetic insulator, and also paramagnetic metal like this. And so question is, such various phases may contribute very interesting novel, extremely nonlinear optical phenomena also. And the possibility of novel nonlinear function via interplay among all the parameters and the strong field. So we did a series of study of high harmonic generation in mode insulator. All right, so I'd like to review a little bit about the what's happening in strongly correlated electronic system under strong field. So Professor Oka predicted tunneling breakdown or multi-insulating state by theory, and this is a frequency, and they he fixed the field strength F0 here, and when we consider the frequency change, so around here we can see the linear response. This is a resonant region. But if you consider the non-resonant region below the band gap, we can see some Keldysh crossover, and below this energy, we can expect very quantum tunneling picture is very valid. And he predicted Davron. Davron is a doubly occupied lattice state, and also Holon. Holon is an empty state. This pair creation occurs under strong field in this quantum tunneling regime. This is quite a little bit similar to the conventional semiconductor Zener tunneling thing, but these bands are not a single electron band. This is a strongly correlated many electron band picture, so we can expect very different things. Actually, in 2015, University of Constance group reported tunneling breakdown of multi-insulating state in vanadium dioxide and using mid-infrared laser or multi-terahertz light. And they obtain very beautiful breakdown to the conducting state after irradiation like this. This is a transmission spectrum. And they obtained some linear dependence to the peak field. This is what is predicted by theory for tunneling breakdown for multi-insulator. And also Keith Nelson group and also Richard Averett group in Boston University at the time, they reported using metallic structure and strong Hertz wave. Also, they can induce insulator to metal transition like this, using the field enhancement of the field between the electrodes. Yes, so they obtain a kind of metallic phase by using strong field. Maybe it's occurred by breakdown things. And very recently, the theoretical works are executed for high harmonic generation. And the Silva group predicted reported time-resolving highly non-equilibrium many-body dynamics in model insulator. And this is high harmonic generation theoretical calculation, but they showed breakdown is playing very important. And here you can see this is excitation light, but the high harmonics occurs in the very beginning of the pulse, like this, they predicted. And depending on the correlation, the spectrum changes a lot. And also, Switzerland group reported using the simple Hubbard model Hamiltonian, they calculated the high harmonic spectrum like this, and they obtained double Holon picture also can be applied to understand the high harmonic generation in the system. And itinerant double Holon pair dynamics is quite similar to the three-step model I mentioned in the conventional semiconductor. They showed in the weak field regime. But other complex phenomena occurs for the strong field they predicted. And for the experiment, very few experiments are reported at the time. And vanadium oxide, so metallic phase, they observed almost nothing. But in the insulator phase, some harmonics they obtained like this. And this is a nickel oxide. This is also predicted as a multi-insulator, but they obtained very anisotropic response. And they showed this anisotropic response is coming from bonding structure. And this bonding oxide and nickel bonding contributing this anisotropic response. But this one also very similar to the conventional semiconductor results. So all right, so now I'd want to have some quite different things from the conventional semiconductor. And we obtained really very novel things in calcium-2 ruthenium-04. This is also a multi-insulator. And we found a scaling law in this material. All right, so this one is what is calcium-2 ruthenium-04. This one is also a multi-insulator, and the phase transition temperature is 357. Below this temperature, the system is going to insulator. And they have orbital ordering around 260, and near transition occurs around 110. But the important point of this material is below this metal insulator transition, so lattice is more changing and increasing anisotropy at low temperatures. So if you look at the lattice constant, some bonding length is increasing, but other direction, nothing happens. So anisotropy is increasing. But the system's crystal symmetry is not unchanged. Interesting thing is the optical gap is changed very largely. This is the metal insulator point, and bandgap energy is around 0.2 eV, around room temperature, but at low temperature, they are going to 0.6. So 3 times opening occurs. Now we focus this feature. All right, so using this system, we measured high harmonic generation using the conventional titanium sapphire regenerative amplifier system, and using dual OPS system, we obtained mid-infrared. And we shined the sample and cooled sample in the cryostat, and using reflective objective lens, we obtained high harmonics. So in reflection geometry. Then we obtain this very nice high harmonics from this system. So please look, this black one, dotted curve. So this is room temperature experiment data. And if you look at 3rd order, 5th order, almost 2 orders decrease like this. But if you cool down to 50 Kelvin, so intensity of harmonics, higher harmonics is increasing a lot like this. And we checked the crystal angle dependence and also power dependence, and all orders, and also not the dependent on the temperature. So almost intensity twice, square dependence like this. this is far from perturbative theory. So the system is in non-perturbative regime like this. And also we obtain very nice crystal angle dependence. And this 45 degree is corresponding to the ruthenium oxide bonding direction. So, and we know such a charge transfer excitation existing in around 1 electron volt. So this resonance is contributing to the high harmonic generation. So this is very similar to the conventional semiconductor. Bonding information is obtained. And now we change the systematically the crystal temperature like this. And this is third harmonic, fifth harmonic, seventh harmonic, ninth harmonic. And interestingly, by cooling down, so many harmonics are increasing a lot. 1 order, 2 orders, almost 3 orders increase of harmonics we obtained like this. But the third harmonics decreases a little like this. Interesting. Then we plotted this enhancement or decrease as a function of gap energy, because we know the temperature dependence of the gap energy, so we can plot this enhancement as a function of gap energy. By taking the log logarithmic plot, we can see very nice linear dependence. This means that this exponential enhancement or exponential decrease occurs in this system as a function of gap energy. Then we changed the excitation laser frequency from 4.8 electron volt micron to 6.5 micron, more infrared side. And we obtain also this harmonics like this. And also we measured temperature dependence, and we obtain very similar enhancement for higher harmonics. Very similar. And we found, very interestingly, if you see 7th harmonics, so of course, excitation laser frequency is different, so emission energy is different. But if you consider this emission energy, we can scale these enhancements anywhere. So if you consider 7th harmonic and taken a ratio between 2 temperature intensity like this, and this ratio is described by the emission energy and also L power. So L is, in this case, 5.6. So everywhere we can obtain this kind of power dependence. So we plotted these 2 color excitation result in the same figure. So I showed the result of using 4.8 micron. And then we also did 6.5 micron, and taking each data and obtain this enhancement factor. This is a ratio between 2 temperatures, intensity ratio. This is enhancement factor. And as you can see, if you plot this enhancement factor as function of emission energy, we can see very nice straight line in log scale. This means that we have some kind of scaling law, and this enhancement factor can be given by this like this. So delta is the gap energy of the system, and T0 is this temperature. So gap energy difference should be the power of this intensity ratio enhancement, and this one is the emission energy, not the order of harmonics. Emission energy is important in this case. This is very different from conventional semiconductor results. And interestingly, this parameter is 0.8 eV, and also this one is 85 milli-electron volt. But this one is very close to the band gap energy at low temperature. But we don't know this. What is this 58 milli-electron volt? Now we consider the systematic theoretical treatment, but we didn't. So we just did a simple two-band calculation for cosine band, two-band. And we did the density matrix formulation and calculated the harmonics. And just changing the gap energy, we calculated what's happening. But this is a result for this simple picture, conventional semiconductor, and just changing the gap energy, what's happening. But we have almost unchanged, no significant. So our observation, very large enhancement at low temperature, should come from electronic correlation or interplay between other order parameters. All right, so time is up. So I'd like to summarize my talk. So we obtained a strong field effect in strongly correlated materials. And we observed high harmonic generation in multi-insulating calcium-2 ruthenium morpho. And we obtained very large enhancement at low temperatures and found a simple scaling law for emission energy and the gap energy. But at the moment, we did not have any theoretical explanation at the moment. So maybe in future, we need really a nice theoretical model beyond simple Hubbard model, because I explained before, some report is appearing using simple Hubbard model, but they cannot say about the enhancement. So really we need some sophisticated theoretical model. And now we are trying to do similar things in several strongly correlated materials, and in several cases, we obtain very similar enhancement. So this feature is very typical or commonly observed in strongly correlated multi-insulators, and maybe we may discuss in total way in near future. Okay, so thank you very much for your attention.
Thank you very much, Koichiro. Great talk, very interesting, very learning a lot of that. Questions, please, Stefan, please.
Yeah, hello. Yeah, thank you very much for this really nice presentation. I have one question. So since you really drive here high nonlinear currents that really make it possible to go even to the 9th order, but in this calcium rutheniate, it's also known that especially at the low temperatures, that you then also drive diamagnetism in this material. At least if you have a static current on this, which is known from the Miami.
Yes.
And my question is now, do you see also HHG from diamagnetic terms? So in analogy to Higgs.
Yes. As you mentioned about this around the antiferromagnetic phase transition, some change occurs or not, and we cannot see any change around magnetic transition point. Also, we checked the mixed crystal. By adding strontium, we can modify the magnetic phase transition temperature, but no change.
Okay.
Yes. So also we can modify using the strontium added system. So we also control the band gap energy, but no very similar things we obtained, but no significant change around the magnetic phase transition.
Okay. Yeah, thank you.
Vishal, please.
Yeah, thank you for the talk. So my question is about the polarization of the HSG from the solid systems. So I assume that these are linearly polarized HSGs. Can we generate the circularly polarized?
Yes. in atomic system, using circularly polarized light, nothing happens. Because of the, yes, but in the case of solid system, so we have some finite angle rotational symmetry. So using this finite angle rotational symmetry, we obtain harmonics, even in the case of circularly polarized light.
But I mean, if I want to have generate HSG, not the income, I don't care what's the incoming beam. I just want to have outgoing HSG as a circularly polarized beam, not the linear.
In the case of threefold symmetry case, we can obtain second harmonic under excitation of circularly polarized light. So that's quietly depending on the crystal symmetry. If the system is threefold, 120-degree symmetry, we can expect the second harmonic.
Okay, thank you.
Thank you very much. Let me thank you, Koichiro. It's a great, very interesting plenary talk.